Welcome, lovers of physics and/or kids that are forced to take it. I'm kidding. Y'all love physics. Here we are. We're going to talk about, we're going to introduce some ideas about forces and Newton's laws, what many of us call dynamics. And we're going to start with a hypothetical, or at least a little exercise in imagination. Let's imagine that this object here, this gray circle, is the only object in a universe. There is some other universe made up of only this object. There's not much going on. There's a single object in this universe. There it is. What will this object do? Well, the answer is not much. The answer is when we say this is the only object in the universe, what we're saying is there is no other object in the universe for this one to interact with. And when we say interact, we mean push or pull on, right? In our upcoming discussions of Newton's third law, we're going to talk about really the nature of force and what force really means. But the spoiler alert is that forces are interactions between objects. So if this is the only object in the universe, there's nothing for it to interact with. There's nothing to exert a force on it. And therefore, what will the object do? The answer is sort of nothing. And the reason is because there's nothing, well, there is no other object interacting with it. There we go. And when we say interacting, we mean applying force to. So if there's no force acting on this object, then the object, quote, does nothing. Well, what we really mean is we mean it continues to, quote, do what it did before. And that's, in a broad sense, Newton's first law of motion. All right. And what it says is, as long as what you normally don't hear with Newton's first law is, as long as there is zero force acting on an object, or really zero net force, that's a huge qualifier for Newton's first law. So this applies. This is for objects with zero force acting on them / exerted on them. What objects will do is they'll do what they were doing before. And when I say do, we're really talking about something we can call state of motion. All right, so what will happen to an object's state of motion? Well, the answer is nothing. If an object has zero force acting on it, then its state of motion will not change. There is no change in state of motion. Well, what do we mean by state of motion? We can simplify that to use by saying the word velocity. So for an object with zero force acting on it, and I should qualify that, zero, what we can call net force. We'll get to the idea of net force in a minute, but what that could mean is, here's an object quite literally with no forces acting on it, but that's the same as if there were an object with forces acting on it like this, where these two forces are equal and opposite. Well, that happens to be an object with zero net force acting on it too. But remember, we said this is an object in a singular universe, or a universe with a singular object in it, and so there is nothing else to exert a force. But that's the same thing. Zero force or zero net force, objects behave the same way. All right, and that is that they don't change velocity. All right, and what does that mean? Well, that means for an object that doesn't change velocity, it can't, so there's no change in, well, speed, which is what lots of us think about as what velocity means, but it doesn't. It means more than that. If velocity is going to remain constant, then an object can't speed up or slow down. It also can't change direction. So objects that are, well, objects that experience zero total force maintain constant velocities. And those velocities might be, or that velocity might be the number zero, or it might be something. All right, and so what you normally hear as Newton's first law is objects at rest tend to stay at rest, and objects in motion tend to stay in motion. What we can really go a little deeper is to say, well, as long as objects don't experience any net force, they maintain constant velocity. They can't change velocity. So force is a velocity changer. It's more than that. It's an interaction between objects, but the result of force or net force is velocity change. So when we say objects at rest tend to stay at rest, okay, that means maintain a velocity of zero. Objects in motion tend to stay in motion. Well, what we really mean is to really say that right without changing velocity. So objects in motion tend to stay in motion at a constant velocity in a straight line at a constant speed. Well, that's the most thorough Newton's first law we can say. Okay? Okay. Now, so what will this object do? Okay, this object is in a, well, it's a regular old universe, I suppose. And this is a regular old, how about we just call it all our universe? This object experiences a single force. Or how about this? This is the sum of all the different forces acting on an object. Force is a vector. All right, so what we could do is say there's a, there's a force to the right, there's a force upward. They happen to combine into this up and to the right force. Or there's, there's 50 different forces that when you add up all their vector amounts, you get this total. So what will this object do? Well, this object, if an object with zero net force can't change velocity, then an object with a net force exerted on it by something else or by other things, this thing will change velocity. This object will / must change velocity. Now, my kids, because we start with discussions of momentum and energy, we know that force can change an object's momentum. We know that net force causes impulse. We also know that net force can do work, and net force can change kinetic energy. Notice that both of those things involve changes in velocity, right? Impulses change in momentum is m delta v, right? Delta k is, well, k involves v squared. So the bottom line is this object will change velocity, and, well, that's not quite the same thing as this other word, but what this object will do is it will accelerate. And acceleration is not change in velocity, but acceleration is defined to be the rate of change of velocity, where acceleration and delta v are both vectors. Velocity is a vector, so delta v is a vector. And if delta v is a vector, then so is a. Okay, so this thing, it follows that for an object with zero net force, there is no change in velocity. For an object with a net force, there is a change in velocity, and the rate of change of velocity is called acceleration. Rate of change of velocity. And notice that acceleration is going to be measured in meters per second, right? Meters per second. Well, that you could write as meters per second times 1 over seconds. So says the rules of fractional algebra, I guess you'd call it. And that's expressible as a meter per second squared. That's the more standard units of acceleration. But these, in my opinion, make it easier to talk about what acceleration means It's how fast velocity changes, by what number of meters per second each second. Okay? So this object will accelerate. Be careful, right? Right. These are not the same. That's a equals. That's one of these equals with a line through it turned vertically. Change in velocity and acceleration are not the same thing. Okay. Um, so says this definition. And this definition says that acceleration is the rate of change of acceleration. I'm sorry, of change of velocity. Okay, so what we can go back here, I mean, the bottom line is that Newton's first law is for objects with zero net force, objects that experience zero net force can't accelerate. That's nutshell Newton's first law. But a lot of people don't really know what the word acceleration means. And you might not yet either, because you might think acceleration means speed up, right? Well, it doesn't. Not in physics. All right. In physics, to accelerate means to change velocity at some rate. And change velocity can happen in lots of ways. Let's maybe get to a few. So we got a few different cases here. Let's talk about what an object will do. Well, case one, right? We've got our universe of a single object. All right. No force is acting on this object at all. It can't interact with anything, and thus, well, let's say that the net force is 0. So what will this object do? Well, one thing is maintain constant velocity. That's the same thing as saying not accelerate. Case two, let's say this thing, okay, well, how about there's a force acting on it like that? And we'll maybe call that the net force. Well, this thing will accelerate that way in the direction of the net force. All right. What we didn't say here is this thing will accelerate, and we can say more than that. In the direction of net F vector. Here's another case where, why don't we say there's, how about a force like this and a force like that, where these forces happen to be equal and opposite. Well, guess what? This same thing, same stuff, is true. Do it. So this object in case 3 behaves just like the object in case 1. In that their state of motion, the velocities of object 1 and object 3 will remain constant. Now, they might not have the same constant velocity, but it will remain constant, whatever it is. All right, case 4, well, let's see. What if we have, how about a thing like this? How about we got a force this way and a smaller force that way, F and F. Well, that means that the net force on this object looks maybe something, well, quite literally, it looks like come on, do it. We take forces, we add them tip to tail, and here's the resultant force, net F. So this thing will accelerate that away in direction of net force. Okay, so what determines what an object will do? That's not a great question. We got to be more specific about what we mean. How an object moves, that's okay too, I guess. But what we know now, what we should be able to state is that net force controls, or is one of the deciding factors in an object's acceleration. Okay. If net force is 0, acceleration is 0. If net force is not 0, then acceleration is not 0. And furthermore, acceleration and net force are always in the same direction. All right, Newton's second law gets into the well, quite literally the equation for acceleration, the quantitative nature of acceleration, and what factors affect it, and in what way. So we'll get there soon. Okay, now let's focus a little bit on objects that don't accelerate. So, AKA objects I'll say upon which net force equals 0. Ooh, here's a good vocabulary word. AKA objects in what we call equilibrium. Same. Equilibrium means net force is 0. So, well, okay, like in case 1, yep, look, no forces. In case 2, how about this? F and F equal an opposite. Or how about case 3? We could even do like, how about we had this force, and well, let's see, and that force. Notice that these 3 forces add up to 0. Here's 1 and 2. Watch, I can take these 2, clone, put them over here, ungroup them, ungroup. Watch, take this one. We can add these forces tip to tail. I'll take this one and clone it. Put this one here. Oh, I didn't do very well, did I? That's a little bit, that's much better. Let me get rid of this one then, delete. So look, since these 3 forces, tip to tail added all up, give you no resultant at all, this means that this object is also in equilibrium. Right? Those are 3 objects in equilibrium. 3 objects upon which the net force exerted is 0. Right? So these objects must not accelerate. Not accelerate. Same as maintain constant velocity. Same as move in a straight line at a constant speed. All right, remember, velocity is a vector. So a velocity of 20 meters per second north and a velocity of 20 meters per second east are not the same velocity. They're the same speed, but they're not the same velocity. So if direction changes, velocity changes. Okay? All right, here's an object not in equilibrium. Let's do this. Let's say, okay, let's just be pretty simple here. Let's say 10 newtons this way, and that looks like what, 3 newtons this way. Well, let's see. Let me change that. Don't draw that yet. Let's say this. Watch this. You'll recognize this, some of you. Let's say there was a object with a force acting on it this way of 8 newtons and a force acting on it this way of 6 newtons. Well, guess what that behaves the same as? It behaves the same as if we took those 2 forces, 8 and 6, and added them tip to tail. Well, here's the net force. And guess what that net force is? Well, I gave you a handy dandy triangle there. 6 squared plus 8 squared is 10 squared. Right? We're employing some geometry to figure out the magnitude of the resultant of that force. And this happens to be, I happen to know, a 37-degree angle. All right, so those 2 objects behave the same exact way, this one and this one. A force of 6 newtons up and 8 to the right is the same exact thing as a force of 10 newtons that happens to point at an angle of 37 degrees, so says trigonometry. All right, let's say we wanted to put this object in equilibrium. It's not. This object is not in equilibrium because, look, there's the net force acting on it. All right, if we want to put that object in equilibrium, well, what we would have to do, notice we have a 8 and a 6, the resultant of which is 10 up and to the right. Well, if we want to put that object in equilibrium, here's how we do it. If you want to do it with one force, we take that one force that's equal and opposite to this resultant. Now this object is in equilibrium, which behaves the same as, yep, this with no forces acting on it at all. We call this equilibrant. An equilibrant is a single force that puts an object in equilibrium. So the 10 newtons is the equilibrant of the 6 up and the 8 to the right. The 6 newtons up is the equilibrant of the 8 newtons to the right and the 10 newtons down to the left at 37 degrees from the horizontal. Any one of those forces is the equilibrant of the other two. Okay, there? Okay. Now, let's talk about different effects of acceleration. All right, so we're going to take 3 different cases where in each case we're saying the object is initially moving upward. And what we can do here is let's apply a net force like that. We're pushing the object, quote, up while it's moving, quote, up. All right, well, what does this thing do? This thing speeds up. Hopefully you can accept the fact that if an object is moving and is pushed in the direction that it moves, that it will speed up. All right, as opposed to this case here, where we say an object, how about experiences a net force like that? It's moving, quote, upward, but being pushed, quote, downward. This thing slows down. And so, yeah, we think of this as acceleration. But guess what? Slowing down is acceleration. In physics, slowing down is acceleration. If an object's velocity changes, the rate at which the velocity changes is what we call the acceleration. So this force will make this object's velocity change at a certain rate, and therefore this thing will have a certain acceleration. So it's okay. We don't, well, maybe some teachers do. I will never say decelerate. All right, slowing down is acceleration. All right, if we were to say that this is the positive direction, well, this thing has a negative acceleration. Remember, acceleration and net force point in the same direction. This force, if upward is positive, this force points downward. Well, there's a net negative force in this thing. This thing will have a negative acceleration. And there's a case 3. What if the net force looked like this? Well, at this instant, right, we can't say, you know, for a while afterwards, maybe later, but right now, because this thing is not being pushed this way at all, it's not being pushed that way at all, it can't do this, it can't do this, but this thing does have to accelerate, but it can't change speed. But remember, velocity and speed are not the same thing. This thing changes velocity without changing speed. This will do, whoops, this will right now change direction only. Now, later, you know, an instant later, this thing will likely now have sped up and be moving somewhat to the right and being perhaps still pushed to the right. Then it will speed up to the right. But at the instant shown in this diagram, the only thing we know this object is going to do is change direction. Okay? So all of these things, these are the 3 ways that an object can accelerate. Speed up, slow down, change direction. No, not in that order. Okay, those are all acceleration. This is the one that people forget. right? You'll see multiple choice questions where you say, hey, here's a bunch of things an object might do. Which of the following shows an object that's accelerating? And you'll miss the one that says change direction because you only think of acceleration as change in speed, but acceleration is rate of change in velocity. Okay? So we've talked about the fact that, well, what an object, quote, does, really the motion of an object, what happens to the motion of an object depends on how much force acts on an object. With no force acting on an object or zero net force acting on an object can't change its velocity. An object can't accelerate, right? And we defined acceleration as the rate of, careful with that, the rate of change of velocity. Acceleration is not change in velocity, it's the rate of change of velocity. We looked at a few different cases of what net forces can look like and what their results are. We looked at a few different looking cases where net force is zero, and we defined this term equilibrium to mean net force acting on an object is zero. And here's what has to happen. We talked about a little bit about a couple cases about how to put things in equilibrium if they're not in equilibrium, and what net force really sort of means and how you can construct it. 3 different cases of what acceleration can mean, right? It doesn't mean speeding up. It can mean other things. How to find components of forces, and in a very introductory look into writing net force statements. Okay, so much more to come, but that's a good foundation in Newton's first law and some things about force. Thanks, folks. Bye.